This is on 5.3, talking about the conservation of energy. First thing I want to look at here is that conserved means remains constant. So in other words, what happens like in the preliminary is what's going to happen as like the after effect. So if you started with 16 joules of energy, you're going to end with 16 joules of energy. So for instance, you drop a light bulb and you're able to sweep up just the light bulb pieces, no like dirt or anything like that, then you should be able to see that the mass before broken equals the mass after broken. So that would be conservation or conserved. So in mechanical energy, we have two different forms that we're going to look at. You should remember this from the previous video, that those two different forms of mechanical energy are potential and kinetic. So ultimately what we're looking here is ME, mechanical energy, initially equals mechanical energy finally. So MEI equals MEF. This is the equation that you're going to want to start with. So conservation of mechanical energy is only good in the absence of friction. Okay, it's only good in the absence of friction because it is the presence of friction that is going to give you non-mechanical energy. So this equation is good and only used for in the absence of friction, and energy is conserved in this equation, so the total energy remains constant. Okay, the total mechanical energy. Total mechanical energy will remain constant. So what if there is friction present in the system? Conservation of mechanical energy no longer exists because KE is not simply converted to PE. Okay, KE is not converted to PE. Some forms of energy are dissipated to non-mechanical energy. And that dissipation is present in heat, light, and sound. So if the system gives off some heat, if the system gives off some sound, then it is going to be non-mechanical energy. Energy conservation occurs when acceleration varies. When acceleration varies. The shape of an object is not a factor in mechanical energy, as long as friction can be ignored. Now in real life scenarios, we know that friction is not ignored. So since friction is not ignored, that would mean that we want to look at like how aerodynamic something is. Okay, how aerodynamic something is, like the shape of a car. Or also tires. Tires are such a big thing. You know, like here in this example, I have one car that's on grass and one car that's on pavement. So there's obviously more friction on the pavement than there is on the grass. So they're probably looking at like all-wheel drive versus just front-wheel drive or rear-wheel drive cars and the traction control on them. All right, in the presence of kinetic friction, first thing I want you to know is that non-mechanical energy is no longer negligible. You have to be able to take it into consideration. Also, mechanical energy is no longer conserved. So that is PE and KE. Recall though that PE has two different forms, GPE and EPE. So let's fill in this flow chart together here. First thing that we have is energy. Energy has two different forms. The first form that I want to remind you of is non-mechanical. And non-mechanical can come from heat, light, and sound. So technically, non-mechanical energy is the dissipation of mechanical energy to form heat, light, and sound. So opposite of non-mechanical energy is mechanical energy. You guys can figure this out. There are two forms of mechanical energy, right? Kinetic and potential. So which one do you think is on the left-hand side here? Which one do you think is going to be right here because it has no other parts of the flow chart with it? That is going to be kinetic energy. And just to review here, your equation is 1/2 mv squared. Whereas this is going to be potential energy, in which potential energy could be either gravitational potential energy, which is GPE equals mgh, whereas h is the value that's going to change your GPE, or you could also have elastic potential energy, in which EPE equals 1/2 kx squared, where it is your distance that is going to determine your EPE, or help influence it for the least. Please make sure you do review this chart. This is a really good summing it up slide. So your sample problem here says that starting from rest, a child zooms down a frictionless slide at an initial height of 3.00 meters. So your initial height is 3.00 meters, and she is starting from rest. And her speed at the bottom of the slide you're trying to figure out. Knowing that her mass is 25.0 kilograms. You also know what the final height is. Well, if she makes it all the way to the bottom of the slide, then the final height of the slide is 0. And you also know that g is 9.81 meters per second squared. So you can figure out what her final velocity will be from this problem. So you want to start off with MEI equals MEF. And you want to be very specific here, guys. KEI equals GPEI, right? It's not elastic potential energy. It is gravitational potential energy that we're talking about. And KEF equals GPEF. Can you immediately cross any of these out? Yes, you can. Oh, I apologize. That should say plus. Okay, so you can cross out your GPEF because your final height is 0, and you can cross out KEI because your initial velocity is 0. Therefore, we have mghi equals 1/2 mvf squared. Rearranging this, we're going to get mghi times 2 divided by m square rooted is going to give us vf. Well, we can make this even more of a simpler equation by saying the square root of hi2 equals vf. M's cancel out. So the square root of 9.81 times 3.00 times 2. You can pretty much figure that one out in your head, right? 10 times 6. So you should be about 60 and then take the square root of that. The actual calculated answer is 7.672, in which your final answer is 7.67 meters per second for a final velocity. So then you'd want to work on your practice E problems, but we are now going to move on to your F, which is going to be on power. So here are our power notes. First thing we want is our definition of power. Power is defined as the rate at which work is done. It's also defined as rate of energy transfer. So your equation is power equals work over delta T. Your work over your change in time. So if you want to break this down, you have power equals work over delta T, which equals FD over delta T. So your units for power are going to be in watts. This watt is equivalent to joules per second. So a watt is equivalent to a joule per second, right? Work is in joules, time is in seconds. But you can even break this equation down. You can break this down one more step further, and it's just simply called the alternative equation. Your alternative equation, once again, power equals work over time, whereas work is FD over time, whereas D over T is velocity. So your alternative equation is power equals force times velocity. Think about this, a machine which is strong enough to apply a big force to cause a displacement in a small amount of time is a powerful machine, because a lot of power would be a lot of force and a little bit of velocity. Think about the relationship between the variables here. Okay, something else that we're going to talk about is horsepower. It's an alternative unit for power in which 1 horsepower, which really there isn't an abbreviation, you just have to write the word out, equals 746 watts. Okay? the wattage of a light bulb in your house, okay? And think about how many light bulbs it would take for this 505 horsepower Corvette engine. This is a 505 horsepower. Wow, okay? So we'd have to take 746 times 505, and that's how many watts. Okay, that's how powerful that engine is. Pretty interesting there. So this equation here, or this question here, is mass of 193 kilograms. It wants to be raised 7.5 meters at a constant speed in as close to 5.0 seconds as possible. Power ratings are 1 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. So how powerful do we want to deal with this so that we can figure out, well, which lever does the operator want to pull? So power is work over change in time, which is really F times D over T, which is really talking about F of G, right? Because you're trying to raise this object, times D over T, which becomes mg times D over T. Okay, so that's the rearrangement that we want to deal with, which is going to give us 193 times 9.81 times 7.5 divided by 5.0. Throw that in your calculators. Also, I apologize, G equals 9.81 meters per second squared. Should have been another given over there. So in your calculators, 193 times 9.81 times 7.5 divided by 5.0. Calculator should be reading 2,839.9, which really is going to be 2.8399 kilowatts. So the closest one that you would want to pull to be able to raise it within those 5 seconds would be the 3.5 kilowatt motor. If you want a calculated final answer, your power would be 2.8 kilowatts. Okay, please work on your practice F problems, remembering that the answers are on Miss Arter's teacher page. We are done with chapter 5.